Thank you for joining us for our webinar, How to Optimize Your Models with Intelligent Artificial Intelligence Experimentation, brought to you by MLconf and sponsored by SigOpt. I'm Joe Fleischer, and I'm excited to moderate our webinar. Before I introduce our guest speaker, I would like to cover a few quick housekeeping items. During our webinar, as you can see, we will display slides, which you will be able to not only view in your console, but also download from the handouts section of your console. Also during our webinar, you are welcome to type your questions and comments within the Q&A area of your console, and we'll plan to address your questions toward the end of our webinar. Now, following the presentation from our guest speaker, whom I have indicated I'll introduce shortly, and right before we address your questions, we'll plan to pose a polling question to you, and we look forward to your responses. I should also point out this webinar will be recorded, and we will email you when the recording of the webinar is available. At this stage, I'd like to tell you about our guest speaker, Scott Clark, the co-founder, former CEO, and current general manager of SigOpt, which Intel acquired in November 2020. Scott leads SigOpt's ongoing efforts to build a product and vision of an intelligent experimentation platform that accelerates and amplifies the impact of modelers everywhere. Scott has been applying optimal learning techniques in industry and academia for years in areas that include bioinformatics and production advertising systems. Indeed, before co-founding SigOpt, Scott worked on the ad targeting team at Yelp, where he led the charge on academic research and outreach with projects including the Yelp Dataset Challenge and open source metric optimization engine. Indeed, it is now my pleasure to turn the floor over to Scott Clark, General Manager of SigOpt. Please give a warm welcome to Scott. Thank you very much.
Excellent. Thank you so much. I appreciate it. And thank you all for attending today, this morning, afternoon, or evening, depending on where you are. So it's my pleasure to chat with you today about intelligent experimentation. In this presentation, I'll talk a little bit about what that means, the solution that we've come up to help solve some of these problems, and then I'll end with how you can use it for free today with only a few lines of code to get all of the goodness that I'll talk about at the first half of the talk. So again, looking forward to answering questions at the tail end. Feel free to just drop them in chat throughout, and we'll address them at the end. But first up, I'll tell you a little bit about how I got here today. So as was hinted at in the introduction, I've been working on this problem for more than a decade now, stretching back to some of my PhD work at Cornell, where I really found all of my colleagues suffering from the exact same problem, regardless of what field they were in. And it was basically a lot of great work was put into building great machine learning models or scientific computing models or whatever it may be. But the end of every project was always this tedious experimentation, this tuning and tweaking of various parameters or hyperparameters or architecture parameters in order to get better results, which ultimately led to better papers, better conferences, etc. A lot of time this work didn't require any specific domain expertise, so it was often left to the grad student to try to do this via brute force, trial and error, or what we jokingly called grad student descent, where you would just try different things and hope for the best. After graduating, I saw the exact same problem at Yelp. There, it was advertising systems, search systems, spam detection systems, and the result of getting this experimentation right wasn't a slightly better paper or conference. It meant a lot of money to the bottom line if you could tune these systems to get to their peak possible performance. This led me to open sourcing the metric optimization engine, one of the first Bayesian optimization open source packages 7 or 8 years ago now, where I rapidly found out that this is an incredibly pervasive problem around industry and has only become more so over the last 7 or 8 years, which we experienced as a venture-backed company and now as part of Intel. And over this decade, we've not only poured a lot of time and energy and research into pushing this field forward, but we've also built a platform that really empowers teams to get the most out of their experimentation. This comes from designing better experiments or asking better questions, to exploring their models in a more robust way to gain better understanding, and ultimately optimizing those models to get to the best possible results. My goal was to never have another grad student waste a bunch of time and energy or government supercomputer hours just blindly trying to do this experimentation, but really giving people the tools to empower them in order to get the most out of what their expertise can actually bring to a problem. So SigOpt does this by just bolting on top of machine learning, deep learning, reinforcement learning, or high-performance computing models, allowing people to tune, track, and ultimately optimize all of the different experimentation that goes into building these models. It's a simple REST API that bolts on top of the infrastructure you already have in place, whether that's in any of the clouds, whether that's on-prem and you just have a connection to the internet, or any hybrid situation that you might have developed yourself. So we take in information about the parameters or the data sets or anything that you want to track. All of this is tracked on our dashboard. And then we can also recommend and inform you on what's the best next thing to try to maximize these outputs or metrics that you may care about within your model. And again, this has been tested in production and tried and true across a wide variety of domains, from over $1 trillion worth of assets under management hedge funds that we work with, US government intelligence agencies, large streaming services, universities, hundreds of different clients worldwide over the last decade. But fundamentally, let me take a step back and talk about what intelligent experimentation itself is. So experimentation is a pretty broad term, but when it comes to modeling, there's a whole bunch of different things that go into it. From just tracking what you're doing and doing things like experiment management, to debugging, to doing smoke tests of specific models, just trying to get something up and running, to understanding the model behavior, convergence, how different metrics affect each other, to optimizing hyperparameters to get to the best possible result before you go into production, and many, many more things. So experimentation is about, once you have an idea, once you've applied your domain expertise and contextual awareness just to try to attack that idea, how do you make sure you get that idea to the best possible state? And this is where modeling is fundamentally different than traditional software engineering, because experimentation is core to that. This is not a linear process. This is something that requires hypothesis testing and applied optimization in order to get to the best results. And the real difference between just generic experimentation and intelligent experimentation is that we want to be working with you the whole time. We want to provide tools to amplify and accelerate and really empower you to get to the best possible results. The difference between traditional experiment management tools and intelligent experimentation tools is, instead of just being something that transcribes what you're doing, the analogy here is just like taking lecture notes from a famous scientist. What we want to do is provide you with a collaborator, someone that you can work hand in hand with, something that you can help influence, that can learn with you, and ultimately guide you to the better results faster and faster every time. And there's really three core pillars to intelligent experimentation. It's not just about optimization and getting the best results, but it's about designing your experiments intelligently, really asking the right questions, exploring the results of those experiments, whether they're just hypothesis testing, trying different data sets and different model configurations, to doing more robust optimization and searches, all the way to ultimately getting to that best possible result once you frame the question the way you want it to. Having a really fast car is great, but it doesn't matter if you don't have a destination, if you don't have a map, if you don't have an idea of what you want to achieve with it. And so all of these things come together to build this intelligent experimentation platform. So at the very beginning of a project, there's a lot of design that goes into it. You're choosing the data. You might be doing different feature transformations, either supervised, semi-supervised, or unsupervised, cleaning the data, doing feature engineering, etc. As data sets get larger and more complex, and computer vision and natural language processing, there's more and more things that you can do upfront to manipulate that data. It's not just a vector with a binary class at the end, but oftentimes there's quite a bit of work that goes into actually designing what even you're going to feed into a model before you start even training at all. There's also just choosing the model itself. Over the last decade, there's just been an explosion of different types of modeling, from traditional machine learning techniques that have continued to be adapted and specialized towards specific domains, to deep learning, to reinforcement learning, and beyond. And more than just the underlying algorithmic techniques themselves, there's also many different ways that you can attack this problem, from frameworks that are specialized for specific hardware to specific cloud end-to-end platforms. So even just selecting this model, what you want to do yourself, is a big part of just designing that initial hypothesis test of, can I build a model that even starts to accomplish this task? And then in addition to this, again, this is a modeling tool is only as powerful as where you're pointing it. So the best thing about a machine learning or deep learning problem is it can take in a lot of data, and it can help, without doing a lot of manual work, get you to a model that achieves some specific goal. But the worst thing about these systems is it will do that blindly, and it will do that towards whatever goal you set it for. So setting something in the early stages to make sure that you're actually achieving the model that produces the best possible business value for you is extremely important. So trying different loss functions, understanding the trade-offs to the business metrics, etc., is an inherently difficult part of this initial design of experiments. So how do you get all this right to begin with? Well, the answer is you don't. It doesn't matter how much experience you have, you're never going to get this perfect combinatorial set of things correct at the beginning. So the solution to this is to try a bunch of different things and track them, though. Humans are good at many things. They're good at coming up with intuition, seeing patterns, maybe understanding how you've applied a previous technique to get to a specific result before. But one thing that humans are very bad at is doing 10 or 20 dimensional optimization in their head and keeping track of all of these different things as they go. So with a few lines of code wrapping around the models that you're already hypothesis testing today, you can get vast tracking capabilities of SigOpt, seeing how all of these different trade-offs that you made, decisions that you made, even at this hypothesis testing step of design, affect things that you actually care about, go back and reproduce results, augment things that you had tried previously, etc. And so this is really about just making sure that you're understanding kind of all the different things that go into the system. After that, it's about exploration. So now that you've developed a system that you can actually run, that you've tried a handful of different things, now you want to understand how you can actually take that and turn it into something that will produce value. So running is great, but producing value is even better. And this is way beyond just setting model.fit or just kind of blindly training a model. There's a lot of things that go into deciding what metrics really matter. They need to be efficient to compute. They need to actually extrapolate to unseen data. They need to be able to actually produce results. And then ultimately, they need to make you money. So when it comes to a machine learning model, again, there's many different decisions that you can make up front around what you're actually shooting for in the training stage, from simple L2 loss functions to more complex, maybe simulation-based approaches in algorithmic trading. This comes down to what are you actually trying to make the data do as you're training. But after that, validation metrics start to become more and more important. And even before that, the training metrics themselves are not all created equal. Even coming to the exact same end result might create a completely different model based off of how you got there. So especially for more complex reinforcement learning or deep learning or even some simulation-based techniques, getting from point A to point B is great, and point B might be the goal. but getting there in a straight line is very different than getting there in a very chaotic way in terms of reproducibility or in terms of being able to extrapolate that to unseen data. So tracking all of this along the way as you're designing, as you're exploring, again, is incredibly important. The validation metrics themselves are what happens after you've done the training. So now you've designed an experiment, you've got something up and running, you're starting to get some understanding about what you want to look at, but then how does this actually start to affect a proxy for what you care about in the real world? So whether you're doing a holdout data set, cross-validation, or you have some completely different way of measuring some expected performance, this is often the meat of what actually matters. So what metrics, what sets of metrics, what combination of things actually correlate to whatever you care about in the end state, in the real world production. So again, this is something that you can track dozens of within SigOpt, look at all of the different trade-offs of. This is, again, at this stage, all about exploration, all about kind of understanding how all of these different trade-offs influence each other. The fourth type of metric, and this is something that we've put a lot of research into, we have a lot of papers and patents around this, is how do you understand guardrails on your metrics? So there might be some things that you just want to increase, like accuracy, click-through rate, etc. But you might have some business constraints that you need to adhere to as well. So there might be a maximum throughput or minimum inference time, or it needs to fit on an IoT chip. Like you want the best possible model, but you need it to be able to meet some very specific constraints. After those constraints are met, then you just want the best possible thing. But understanding how those constraints affect the response surface of the metrics you actually care about, understanding how to get there as efficiently as possible, is often an incredibly complex problem. So two examples here are in the upper right, there might be some window of these two metrics, the x-axis being the size of the model and the y-axis being the accuracy of the model, where you want the highest possible accuracy, but within a specific constraint of the size of the parameters. So there's some threshold on accuracy, but then the model itself needs to be a specific size. Or on the left here, there might be a very specific edge device that you're trying to fit this on that has a tight window of how much it can actually fit into memory. And then beyond that, you want the highest possible accuracy. But just getting a super accurate, super big model actually doesn't solve your business problems. So again, understanding not only the set of metrics that you care about, but also what specific constraints you might have on either optimized or unoptimized metrics can have a huge impact onto what actually matters when you take this to production. Which is the final set of metrics that are important to explore, the actual production metrics themselves, whether this means running an A/B test on a handful of different variants of the model itself to maximize something like click-through rate, to running a handful of different algorithmic trading strategies on the real market to determine what their actual returns will be. Keeping track of these metrics, being able to explore and correlate them back to the original training metrics and validation metrics is incredibly valuable, not only for getting the best model this time, but also doing better experimentation later on for the next model. So again, the goal here is you're not going to get everything right perfectly to begin with. Track everything, store everything, explore everything. This is about gaining understanding as you go, trying different things, but really making sure that you look at the wide variety of different inputs and outputs that go into making your model experimentation as efficient as possible. And the final pillar here is about optimization. So this is what SigOpt was designed around, that open source optimization from several years ago, and it's been built up into an ensemble, a collection of many different Bayesian and global optimization techniques behind our API today. Again, the idea is once you've built a model that can run, you've designed a model, once you've explored it to understand what it is you want to shoot for, now how do you get to that best possible state as efficiently as possible? How do you trade off exploring different configurations and exploiting the information that we get from that in order to drive you to the best possible results in as few computational hours as possible and as few wall clock hours as possible, just as efficiently as possible. So the way that this works is you define your search space, you define the metrics that you care about, you define the constraints, the metrics or the parameters, and you basically say, this is what I'm shooting for. SigOpt provides a configuration or set of configurations if you can run this in parallel, asynchronously or sequentially. And you evaluate how well that's done against the metrics that you've learned to care about from the exploration phase. We see how well those configurations performed, learn from that to give you the next set of configurations to try and repeat. And this optimization feedback loop, again, guides you to better and better results, typically several orders of magnitude more efficiently than a more naive brute force technique. And in practice, we've seen this to be about an order of magnitude more efficient than a single Bayesian optimization approach or a single approach from the academic literature by kind of pulling all of these things together behind our API. An important thing to do as well here when it comes to optimization is making sure, again, that you're looking at the full spectrum of all of the different things that you care about. Very rarely in the real world do you only care about just accuracy or just an F1 score or something like that. Oftentimes you might be able to publish an academic paper, and I'm guilty of doing this myself, by just overfitting to one specific academic metric. But in the real world, you often have many different trade-offs that you're trying to make. You want the fastest model, but also the most accurate. You want the highest return on your investment, but you also need to be able to trade enough for it to be a worthwhile strategy. There's always things that you're trying to trade off. And instead of trying to come up with one composite metric that kind of takes all this into account, SigOpt allows you to be able to optimize many of these different metrics simultaneously. Understanding this kind of Pareto frontier or this trade-off of efficient trade-offs between these metrics. So I want to be able to understand how accuracy affects inference time, and then based off of what's actually feasible from the model, select along this efficient trade-off between the two to get to the best possible results. And there's a lot of these great techniques built into SigOpt, but we also don't require you to use SigOpt itself. There's many great optimization packages out there that have been building upon some of the early work in the field, and we allow you to bring your own optimizer or trade off between optimizers. It's not about us versus them, it's about everybody being better together, having a single system to do intelligent experimentation, but providing many different ways to actually go about doing either the optimization and getting to those results that you care about. So we have a couple examples here of doing kind of more traditional brute force techniques, using different open source optimizers, trading off between optimizers. The intuition here is 2 is better than 1. It's kind of a no regrets move to try many different things in order to get to better results. At the end of the day, though, again, having written some of the original open source in this field and having had a full-time research staff really push the state of the art, including publishing dozens of papers at top machine learning conferences and really understanding applied optimization from all of our industry and academic partners, we've developed a wide variety of advanced features to be able to solve not just the simple problem of I have a couple parameters and I'm trying to get to the best accuracy, but all of the different things that come up in real world, from, again, constraints to conditions to early termination to finding multiple solutions to exploring as efficiently as possible with just very vague constraints on what a good model is. There's many different things that we've continued to develop, and this is an active field of research. And all of these features are available for free today within SigOpt. So again, the takeaway here is experimentation is more than just tracking results. It's more than just optimizing to get to a specific value. It's really about understanding all of the different trade-offs and work that goes into designing experiments to even ask the right questions, exploring experiments to get understanding of your model, and optimizing those experiments to get to the best possible performance, however that is defined for you individually, because every model is different. So as I mentioned at the top of the talk, we've been doing this for many years for many different clients. Numenta is a perfect example of this, who used us to get a very sparse but also very accurate version of ResNet using our multitask experimentation platform or feature, being able to kind of extremely efficiently attack this extremely important problem for them for their production models. PayPal is another big user of SigOpt, being able to take our system to tune their graph neural network problems, accelerating their time to convergence by 40% beyond what they were able to do with other open source techniques, as well as allowing them to really explore the way that they think about metrics more generally as well. Instead of, again, just blindly shooting for one thing, tracking everything, putting constraints and putting optimization across a wide variety of different things can lead to fundamentally new and novel results. And then ultimately, again, a lot of our bread and butter over the last decade has been the optimization ensemble itself, the system that we have behind our API to guide you as efficiently as possible to these best results. So an example here is 2 Sigma has used us for many years to optimize a wide variety of different models within their systems. And they found that this is significantly about an order of magnitude more efficient than using, again, a single open source optimization approach. And again, with SigOpt, we allow you to bring your own optimizer. So it's not just us versus a single approach, but you can bring all of those approaches and us together to ultimately get to whatever results that are most important to you. So that's intelligent experimentation. That's kind of a whirlwind about kind of why it matters and different techniques and tools that we've developed in order to help attack this problem. Up next, I'll show you explicitly how to do this with a few lines of Python, really making sure that showing you just how easy it is, no matter what modeling system you have, to just bolt this on top and immediately start getting all of the benefits of intelligent experimentation today. So first up, I'll frame up the problem here. This is kind of a classic machine learning problem. We take the breast cancer data set that's available in scikit-learn. It's got 569 samples, 30, that's a length 30 vector. And the idea is you're trying to do binary classification of malignant or benign cancer. We're going to use one of the most popular packages in the world here, XGBoost, in order to do this classification. And we're going to tweak this from the kind of the standard kind of intro to Kaggle or intro data set, in the sense that instead of just tuning for accuracy, we're actually going to try to maximize recall for each label. So we want to have how many of the true and false, or the malignant and benign correct answers were actually classified as such within this data set. So what you can see here is just a simple Google Colab notebook. We're grabbing the data set with just a few lines of code here. Again, we're able to start logging information to SigOpt. So we're keeping track of what data set we used, what model we used, etc. Then we were actually training the model, and then tracking the actual metrics at the end. So the different classes, their precision, recall, etc. All of this is being pulled together. And this is maybe where some experimentation is being done today, where you might have something like this. You might be keeping track of this in a spreadsheet or a notebook or something like that. But again, typically what we see is people will do something like a manual exploration of the parameters to begin with. Again, with just a slight modification here, we're able to now all of a sudden start tracking this within SigOpt. So now at the top here, we're tracking kind of metadata parameters about the experiment itself. In the middle here, we're tracking different hyperparameters to XGBoost. And at the bottom, we're tracking a variety of different metrics. And this is where we can start, again, doing whatever we were doing historically. We could do a grid search, we could do a random search, we could do a manual search, just manually tuning and tweaking some of these hyperparameters. But instead of just trying to do this manually in your head in terms of understanding all of these trade-offs, now all of this data is being logged to SigOpt. So with those few lines of code, now we can look at how accuracy is being affected by these various parameters, how all of these different things come together to ultimately produce a variety of different metrics, from the support to the recall to the F1 score, et cetera. And all of this is being tracked in a single dashboard. And this really allows us to start to gain insights as we explore. So we've designed the experiment to track everything and to try a few things, but now we can start to notice patterns. Like when we look at all of these individual runs, we can see that the actual accuracy of the set can vary somewhat widely here, from around 90% to around 94%. Maybe for the specific task, we have some business constraint, as I mentioned before, where we might need at least 95% accuracy for this even to be a viable model. And then beyond that, we're trying to maximize these recall numbers. And so what SigOpt allows you to do, again, is taking that original model that was just a few lines of code, and now start to design an experiment, an optimization experiment around it. So we can tune the estimators, the depth, the learning rate, et cetera, different integer or continuous parameters or even categorical parameters, and start to tune it towards a variety of these metrics that we've been just tracking before. So there might be specific things like the accuracy, this first metric here, where we just want to put a constraint on it that it needs to be above 95%. Then there's a handful of other metrics that we just want to store. We just want to continue to keep track of these as we go. But then ultimately, as described in the problem example at the beginning, we actually want to optimize the recall of both the correctly identified benign and malignant tumors. So now we've designed this experiment to tune these 3 parameters. We're going to try 30 different configurations, and we're going to go through this optimization feedback loop to maximize both those recall metrics while also putting a threshold on the accuracy metric. And what this looks like in the platform is very rapidly this experiment starts to get populated. And we can see a variety of different results over here on the right. The gray dots here are specific configurations that did not meet the accuracy threshold. The blue dots are points that met the accuracy threshold, but are not on this efficient Pareto frontier of this kind of best possible trade-off between the 2 different types of recall that we're trying to optimize. And the orange points here are satisfying not only the underlying constraint of having at least 95% accuracy, but also have this efficient trade-off of you can get no better recall in one metric without sacrificing recall in the other metric. So these are the points that then we can take that satisfy the business constraint, are optimal for the actual underlying metrics that we're trying to optimize, and then we can further explore these models in order to understand which one we should actually put into production when it comes to this underlying data set. And again, all of this is accomplished with just putting a few lines of code around a model that you might already be running today, whether that's XGBoost or a much more complex deep learning system. And then, as I mentioned before, we can look at different trade-offs between these, different learning rates, et cetera. These best points now that we've designed this experiment to optimize towards them, we can then start that feedback loop again of designing a new experiment, exploring kind of how learning rate affects all of these different parameters, et cetera, and going on from there. So ultimately, again, the idea is to have a lightweight tool to wrap the models that you're already running today, to be able to design these experiments, track everything, a dashboard to be able to do those analytics and exploring all of the different results, and then ultimately optimizing towards what you care about after you've gone through the process of setting up a target. Now you want to hit that target as efficiently as possible. So a couple things I want to call out here before we move on to questions. One is that SigOpt is completely free. It's free forever. You can sign up for an account today with sigopt.com/signup and start running these examples right away. We have many different examples to use, but please try it out. Let us know what you think. Second is that we have a user conference coming up on November 16th. We have a lot of great speakers from some of our academic and industrial collaborators, from some of which are listed here, but it's going to be a great overview of how each one of these teams has used this design, explore, and optimize paradigm to either produce a better paper or a better model for their industrial use cases. So I highly recommend checking this out. We're going to have machine learning, deep learning, high performance computing, a lot of different approaches that you might be able to get some intuition about or some inspiration from. So with that, I'll pause, and I think we're going to do the poll, and then I look forward to doing the questions.
Well, thank you so much, Scott, and we will be moving into our poll. We also have some time to address some great questions from attendees, and I'll also reiterate each of those links that Scott had so kindly shared regarding access to tools from SigOpt, as well as SigOpt's annual or SigOpt's upcoming user conference, I should say, as well as MLconf's upcoming conference. But in the meantime, I think we'd like to now, as Scott mentioned, pose our polling question. And so what we're going to do now is pose this question to you. And what we want to find out is which tools you use today in your modeling workflow. You can select all that apply. And from top to bottom, the choices are experiment tracking tools. We've given some examples here. Hyperparameter optimization tools, but not necessarily open source. Open source hyperparameter optimization tools, or distributed orchestration tools. Now, as I mentioned, you can feel free to select all answers that apply. We'll give attendees sufficient time to respond. If none of the above apply, that's fine. You can select that choice. But again, if you are using any combination of these tools, we do invite you to select all that apply. And as I've mentioned, we'll give attendees sufficient time to respond, and then we will reveal and comment on your findings. Again, just to give attendees sufficient time to respond, I'm going to reiterate the question and choices. We want to find out which tools you're using today in your modeling workflow. We do ask that you select all that apply. And again, just to recap quickly, from top to bottom, the choices are experiment tracking tools, hyperparameter optimization tools, but not necessarily open source hyperparameter optimization tools, distributed orchestration tools, and again, if none of the above apply, then you can select that choice specifically. And we'll give attendees, as I've mentioned, enough time to respond, and then we will reveal how you have responded. And I'd already acknowledged just at the outset that right now a plurality, and actually a majority, are not necessarily using any of these tools. But if I were to bring up a plurality, if you will, I would point out that experiment tracking is taking an early lead, or taking the lead, I should say. And before we address, as I said, some great questions from attendees, I would like to perhaps give attendees maybe 1 or 2 seconds to respond. And then I'd love to hear your thoughts, Scott, specifically regarding this question in terms of responses that you've observed, or what you've observed in your experience. So again, we have given attendees opportunities to respond. We're now going to close this poll, and I do want to acknowledge that a plurality of respondents have indicated experiment tracking when indicating tools that they're using. I am very curious, Scott, just to get your perspective here, and that is when you've posed this question, when you've worked with various organizations, what have you observed? In other words, what has been the most prevalent response, factoring in whether or not, for example, hyperparameter optimization tools are open source?
Yeah, excellent. So thank you all for responding to the poll. Yeah, we've seen a wide variety of different things in academia and industry. I'd say the biggest commonality is that there is no commonality. Even within organizations, even within sometimes small teams, different people use a wide variety of different tools. They might have a specific open source optimization tool that they use. One person might be using one experiment tracking tool, one person might be just doing it in a spreadsheet or whatever it may be. The biggest thing that we've seen is that it's still kind of very wide open. And that's really why we've continued to design SigOpt and continue to adapt SigOps to be more open itself. Allow people to take in the different open source optimization techniques they might already be using today, they might already be comfortable with. Allow them to do all of the aspects of intelligent experimentation together instead of trying to cobble together a bunch of different tools to do this individually. And by doing that, not only does it allow you to do your job better, but it allows you to standardize among your team or organization instead of having this very disparate way of doing things across the board. So over the last 7 years, we've seen an evolution of nobody doing optimization to people doing some optimization. Maybe it was grid search or random search to starting to use the wide swath of open source tools that have really sprung up over the last 4 or 5 years. But the main thing, again, is that everybody's doing something a little bit differently. And so by having a single intelligent experimentation platform that can help you with these problems, we're hoping to help bring these people together, not switch off their tools necessarily, but really bring their tools and have something that's greater than the sum of its parts.
Well, thank you very much, Scott. I think we have time for maybe 1 or 2 questions from attendees. And one attendee asks an intriguing question, in my opinion, and that is asking you, Scott, are there any trade-offs to keep in mind when determining whether or not, or when using hyperparameter optimization tools, whether or not to go with open source? Are there any trade-offs that one needs to keep in mind? If so, what are they?
Yeah, great question. Yeah, there's some great open source out there. We contributed to a lot of open source out there. I'd say one trade-off is even just how long that open source will be around, whether it's kind of just academic open source, which again, I'm guilty of writing and abandoning myself throughout my academic career, whether it was meant to solve a very specific problem and publish a very specific paper, or whether it was designed to solve a larger industrial problem. Open source is great because you can actually pull open the hood and check in and see how every individual thing is working and potentially modify it yourself. But in all reality, what we've seen with many different firms around the world is they don't actually end up doing that. What they really care about is not that they can go in and write their own kind of custom acquisition function or something like that. What they really care about is having a tool they know works, that's supported, that they know they can rely on, and that they can ultimately just use to get to the best possible results. So there's a couple of different trade-offs. Obviously, open source allows you to kind of customize and really understand the depths of it. And if that's really important to you, then I highly recommend continuing to do that, creating a custom optimizer, and then using the other intelligent experimentation tools provided by SigOpt and just bringing your own optimizer or trading off between that and our optimizer. But if you just really care about something that's designed for real world problems that you can just trust out of the box, that's just going to work and work very quickly and robustly, then I would recommend using a more hosted and supported tool.
Thank you very much, Scott, and I think the attendee appreciates your answer. I think we may have time for one more question from an attendee, and this has to do with orchestration. So, with regard to perhaps drawing conclusions from experiments and keeping that in mind, what are your thoughts in terms of best practices? Not only using the tool and using the capabilities of the tool, but also deriving conclusions. In other words, to what extent is human judgment, or in what ways can human judgment augment what one gathers from experimenting and testing various models?
Yeah, so this is really what intelligent experimentation is about at its core, to be honest. It's about not just blindly trying to get to the best possible accuracy or whatever it may be, but allowing more of that human intuition to go into the process, whether that's designing specific custom metrics, putting these guardrail metrics up, kind of qualitatively exploring the results to see trade-offs that you might not be aware of like, oh, hey, I was able to push up these metrics a lot, but then the recall dropped incredibly in this other area. Like the model ended up just overfitting to a specific class because I didn't do stratified sampling or something like that. And so that human intuition is incredibly important. And that's really a lot of the philosophy of how we do product development at SigOpt. This isn't about replacing the expert. This isn't about taking the human out of the loop when it comes to experimentation and optimization and just automating everything away. This is about augmenting the expert. This is allowing them to bring their expertise in an amplified and accelerated way to really understand what it is they really care about and get there as efficiently as possible. So it's really about, enabling and empowering, because there's many different things that can go wrong if you're just blindly letting the machine do what it is that you originally set it out to do.
Well, thank you very much, Scott. Before we conclude, and really have enjoyed learning from you, I'd like to direct attendees to several links. So the first link I want to direct you to, you being attendees, is getting started, as Scott mentioned, with SigOpt in minutes for free forever. And so here is the link, which you can see now. So I just want to bring that to your attention. Again, if you click on the link, and you should be able to open a separate tab within your web browser when you click on this link, but again, want to make sure to invite attendees to first get started with SigOpt in minutes for free forever. Again, you can click on this link to sign up. That's our first link we want to direct you to. And then next, and again, each of these links will appear in a separate tab within your browser. Next, what we want to do is direct you to another item, and that is attending SigOpt user conference. So let me direct you to this as well. And this is a link to attend SigOpt user conference, which is actually taking place next month. And as you can see here, you'll have the opportunity to hear a great variety of talks from experts, Scott, among others, on applied artificial intelligence use cases. And you can click on this link to register. Again, that link should appear in a separate tab within your web browser. So that's the second link we want to direct you to. And then we would like to invite you to register for MLconf's conference next Friday, October 15th. Thank you very much. First of all, I'd like to thank you, Scott, for sharing your expertise. I would like to thank attendees for joining us. I would note, because this webinar is recorded, you will have the opportunity to view and listen to a recording. We'll email you when a recording is available. And we really appreciate your joining us for our webinar, How to Optimize Your Models with Intelligent Artificial Intelligence Experimentation, brought to you by MLconf and sponsored by SigOpt. We hope you enjoy the rest of your day.
Thank you.